In this video, we're going to talk about the behavior that is exhibited by liquids and solids, and that is the incompressible substance model. But before I move on to that, I want to talk about a couple of things, a couple of properties that are related to internal energy that are important in thermodynamics. And one of these properties is called enthalpy. And we've talked about enthalpy in the previous video as well. Um, but, well, basically, enthalpy is uh, given in the form of internal energy plus PV. Okay, so because this relationship is used so often in thermodynamics, that's why it's usually altogether given the name of enthalpy. But what does enthalpy physically mean, you might ask? Well, so just to understand the concept of enthalpy, you need to understand the concept of energy as well. That when we talk about energy, we say that it is a measure of some body's ability to do work, right? Whereas enthalpy is the amount of energy in a certain amount of substance. So, for example, if I'm talking about, let's say, I'm talking about petrol. So, if 1 kilogram of petrol has, let's say, X joules of energy, then 2 kilograms of petrol, let's just assume 2 kilograms of petrol would have twice that amount of energy, right? So it would have 2 into X joules of energy. But they would have the same enthalpy because enthalpy is in terms of, let's say, kilojoules per kilogram, okay, or joules per kilogram. This is how enthalpy is given as. So per kilogram, enthalpy hasn't changed. Energy has changed, but enthalpy remains the same. That is how you can understand enthalpy. That enthalpy is the amount of energy in a certain amount of substance. Okay. Other than enthalpy, there's two other properties that I want to talk about, and those are specific heats, Cp, C subscript P, and C subscript V, and they're defined for pure and simple compressible systems in terms of, so say, for example, if I was to take the partial derivative of internal energy um, based on temperature while keeping the volume constant, okay, then this would be CV. And why am I doing this? Because usually internal energy is a function of temperature and volume. So if I'm keeping the volume constant, I'm not changing the volume, and I'm taking the derivative of internal energy with respect to only temperature, then that would be a partial derivative, right? Um, so that's CV. And on the other hand, we have Cp, which would be a partial derivative of not internal energy, but enthalpy. If we're taking a partial derivative of enthalpy uh, with respect to temperature while keeping the pressure constant, then that is termed as C subscript P. And why are we doing this? Why is this a partial derivative? Because enthalpy is a function of temperature and pressure. Okay. So this is how it works. Um, Another thing, you could imagine, let's say CV here, you could imagine that this is the amount of heat that is required to raise the temperature of a substance of 1 kilogram mass by 1 degree Celsius at a constant volume. So you are raising the temperature of 1 kilogram of substance. And how much temperature are you raising? You're raising a temperature of 1 degree Celsius. And what is the condition for it? You're doing it at constant volume. Okay, so you're doing it at constant volume. This is CV. And CP, C subscript P here, is the amount of heat that you require to raise the temperature of a substance, again, by 1 kilogram of mass, um, again, by 1 degree Celsius temperature, but at a constant pressure. Okay, so I hope this makes things a little bit clear. Another way to, another important thing about uh, this would be, especially C subscript P would be, is that it increases with temperature. So for example, this is a graph that we're looking at for water vapors. And CP, what you would see is that it increases with temperature for constant pressure. So for example, this is a constant pressure line. This is the zero pressure limit. So as I'm increasing the temperature on the x-axis, I would have CP um, increasing as well um, to a certain degree. Okay. All right. So one more important factor here before we move on is the ratio of C subscript P and C subscript V here. And that is something that is called specific heat ratio. So if I was to take, let's say, the ratio of Cp to Cv, then that would be equal to specific heat ratio. And you will see that in some texts, specific heat ratio is denoted by K. In some texts, you will see that it's denoted by gamma. So they're one and the same thing. Don't get confused by its terminology here. It's the same thing. The notation can change, but it's the same thing. It's specific heat ratio. It's the ratio of Cp to Cv. Specific heat at constant pressure to specific heat at constant volume, the ratio of these two. All right, so now we can move on. And oh yeah, one more thing that I should let you in on that will make your life a lot easier when you're dealing with compressed liquid water table is that let's just go to this table, right? So this is the table that you will usually see, the compressed water table. And what you will notice is that, let's say, I keep the temperature constant, okay? So the compressed water table is applicable in this region, right, to the left side of the dome. And let's say I'm looking at, okay, let's say I'm looking at 20 degrees temperature, okay? So I'm looking at 20 degrees, and let's say that it's somewhere here. We have got 20 degrees here, and the saturation temperature is around 223. So let's assume that that point is here, the saturation point. Okay, so if I'm looking at, now I would have constant pressure lines on this curve, right? That's TV diagram. So I would have constant pressure lines. I could have one that could be like this, another one that could go like this. So if I'm, let's say, looking at 20 degrees, let's say I keep the temperature constant here. Now what you will notice is that if you're looking at specific volume, there's not a lot of change, although the pressure is changing. From 25 bars you've gone on to 50 bars, but the change in specific volume is really minute. And you will see this trend for only for compressed liquid water table, that at 20 degrees, for example, it's not really changing too much. If it's 0.9995, it's 0.9984 over here, 0.9972 here. So it's not changing that much. And just like that, you will see that internal energy, you will see the same trend. It's not really changing too much, right? Um, and okay, there's a little bit more change when it comes to enthalpy. Um, but what we usually do is that we assume that if we are in this region, instead of looking at, um, let's say, the table and going through the table and then evaluating, let's say, um, what would be the specific volume or something at different pressures, I can just, at this constant temperature, I can just take the value that is over here, let's say. Okay. So instead of um, having to evaluate um, specific volume or whatever property we are looking at in this region, I'm just going to go onto this curve uh, at the constant temperature line here. And I'm just going to pick up this value, whatever that is, on this saturated liquid line. Okay. So that is just one thing that may make your life a bit easier. Instead of having to go and base it on temperature and pressure, I just need temperature. I just need to look at the temperature, and that's all I need. Instead of looking at the compressed liquid water table, I could just use these equations instead. Okay, so now we can move on to the incompressible substance model. And I'm just going to define what an incompressible substance is. Um, and usually, an incompressible substance is an idealized substance, and it has two qualities. The first is that we assume that the specific volume is constant. And the second is that specific internal energy, we assume that it only varies with temperature. Another thing, important thing, is that you are talking about certain liquids and only solids when you're using incompressible substance model. When I say certain liquids, what I mean is when I'm talking about compressed liquids, just the one that we saw. If you're looking at the TV diagram, the one to the left side of the dome, only those liquids, and obviously all kinds of solids. Those are included in the incompressible substance model. Um, so yeah, so to simplify, evaluating liquids or solids, the specific volume is usually assumed to be constant. That means density is assumed to be constant, and well, specific internal energy is assumed to vary only with temperature. And if a substance fulfills both these qualities, then that substance is idealized as an incompressible substance. Okay, so because we are saying now that the specific internal energy of the substance that is being modeled as incompressible depends only on temperature, what that means is that then the specific heat CV that we just saw is also going to be a function of temperature alone, right? Because what was CV in the first place? CV was a partial derivative of internal energy uh, by temperature, with respect to temperature. So now that we're saying that specific internal energy is varying only because of temperature, so that means that the specific heat CV is a function of temperature alone. It's not a function of temperature and volume anymore. So now I can, instead of writing the partial derivative now, I can write it as an ordinary derivative, and that will be du by dt. Um, Other than this, specific volume is constant, internal energy depends only on temperature, and that means that enthalpy now is going to be, which is a function of temperature and pressure, like we said, it's going to be equal to internal energy, which is a function of only temperature, plus PV. Okay, and these two are only valid for incompressible substances. And now if I was to differentiate this equation over here with respect to temperature while holding pressure constant, what would that become if I'm differentiating enthalpy with respect to temperature and I'm keeping the pressure constant? Then this term is going to go out. This is going to be 0. And this term over here is going to become du by dt. And now if you notice, this part over here is actually equal to CV, right? So the right-hand side is equal to CV. And the left-hand side here, this is the expression that we just previously saw for specific heat at constant pressure. So that means that for an incompressible substance, both the specific heats are equal to each other, and you can just represent them both as C. So this is another relationship that is valid only for incompressible substances. So what that means is that we do not need to distinguish between CP or CV. They can be represented by the same symbols, and usually you have different tables that are given to you that would have specific heats of common liquids and solids. And if you're using, let's say, Shapiro's book, you would have to go and take a look at table A19, and you will be able to see these properties for different liquids and solids. Another thing that I should now mention is that if I'm looking at change in specific internal energy now from this equation, let's say, if I'm looking at change in specific internal energy between two states, that would be, then it would be, instead of du, it would have to be u2 minus u1. And dt can go on to the other side, so it would become u2 minus u1 equal to, and now because I've already indicated that CV is just something that can be represented by C, so it could be C, which is a function of temperature, and dt moves on to the other side, so it's going to be dt and integral from temperature T1 until T2, because we're looking at specific internal energy between two states. So this is the first state, this is the second state. And from here, what I can do is that I can get, if I'm looking at change in specific enthalpy now, then that is going to be equal to H2 minus H1 equal to, well, U2 minus U1 plus, obviously, we have PV over here as well. So it's going to become, at constant volume, it's going to become P2 minus P1. But usually, this term on this side is usually way smaller than U2 minus U1, and we usually neglect it, but you have to be careful with this. So these are the two equations, the two important equations that we need in order for us to talk about the incompressible substance model. This is what incompressible substance model is basically. Okay. all you have to do is you have to evaluate this integral over here now. And well, over here as well, u2 minus u1, you can just plug this equation in here. So this is just going to be equal to this integral again. So you have to integrate both these equations for specific internal energy and specific enthalpy as well. Okay, and once you do that, well, I'll just show you what that's going to be. Okay, yeah, so this is what it's going to be once you introduce those integrals and integrate the equations. You're just going to get u2 minus u1 equals specific heat or heat capacities into T2 minus T1. Another important thing is that this is, you're talking about specific internal energy, but so that includes the mass in there too. But if you were talking about, let's say, U2 minus U1, then you would have to basically, because this is then going to be divided by mass, so mass is going to come onto the other side, and it's going to be equal to T2 minus T1, right? And just like that, you would have to do it for a specific enthalpy as well. Okay, so this is what the incompressible substance model is about. We're just going to look at one small problem, and let me just move on to that. So we have a question here that I'm just going to look at really quickly, just to give you an idea about how you can solve this equation or solve this problem actually. So I'm not going to go through this over here. I'm just going to explain what is happening here. So you have oil in here, and this oil is being burned. So you have oxygen being supplied in here, then you're igniting this oxygen. This oil is completely burnt, and this is a separate chamber in itself. So you have this chamber, and you don't know what all the contents are, let's say, and you just call them chamber contents. And this chamber is being kept in a water bath, so you can evaluate what are the temperature changes that are taking place. And this entire system is insulated. So you have the initial temperature that is given to you, and after the oil has been ignited and equilibrium has been achieved again, you have temperature given to you again, the final temperature. You have the mass of water given to you, and the metal parts are being approximated. The metal parts over here are being approximated as additional water, so you would have to account for that too. So let's just look at this. If I had to write an energy balance for this one, then obviously I would have to go with what is the energy balance. It would be changes that are taking place in the internal energy plus any kinetic energy changes that may be taking place plus any potential energy changes, and then obviously this is going to be equal to heat transfer, if any, or work done into or out of the system. And because we're assuming here that there's no kinetic energy changes taking place, potential energy changes taking place, and we can see that no heat transfer is taking place, no work transfers are taking place. So all that we are left with is changes in internal energy equal to 0. And now the changes in internal energy can take place either for the contents of this inside chamber here, so changes in internal energy of the contents plus changes in the internal energy of the water, right? So I'm just going to represent that by subscript W here. and that's going to be equal to 0. Or I can just take this to the other side, and then this is going to be equal to minus this. Okay, so let's just not look at this right now. And now that we have this, so what we're saying is that because we're assuming that we're modeling water as incompressible, so by definition of the incompressible substance model, I can write the right-hand side of this equation in terms of, well, mass multiplied by the heat capacity into the changes in temperature that are taking place. And that would give me because I'm trying to find out the change in the internal energy of the chamber contents. So this would be giving me the changes in the internal energy of the chamber contents. And now all I have to do is I just have to go ahead and I already know this. This is equal to 2.15 here plus 0.5 kilograms of water. I've got T2 minus T1 as well. What else do I have? Okay, one thing to notice here, this is actually 25 degrees. This is not 258 centigrades. This is 25 degrees. So the change in here is about, let's say, 0.3 kelvins, you could say. So T2 minus T1 is, let's say, 0.3 kelvins. And what else? You need the value for CW here, C subscript W, which you can go ahead and find out from table A19 in Shapiro's book. And you will get some value here for basically these chamber contents. And this would give you the value in kilojoules. Yeah, this would give you the value in kilojoules, and then because you're looking at converting it into kcal here, right, into calories per milliliter. So what you would have to do is that you would have to divide this delta U. You would have to divide it by the volume of oil. And the volume of oil is given to you over here. So let's say whatever value you're going to get from here, you will divide it. So it's going to be in kilojoules. You're going to divide it by 0.1 milliliters. And then you're going to multiply it again with, go ahead and check what the conversion is for kcal, and it's around 4.1 kilojoules, I think. So you would have to convert this, and then you would get the value over here in terms of kcal per milliliters. Okay, and this is just to give you an example. This is something that you usually see on your cooking oil containers or bottles too, where it says that it gives you the kcal values, the calorie values for serving sizes of tablespoons or teaspoons. So usually it's given per tablespoon, and a tablespoon is usually considered as equal to 15 milliliters. So if, I don't know, maybe someday you need to do this, you could just multiply it, the value that you will get here, into 15, and you would get the value in terms of calories per tablespoon. Okay, so this is just to show you how you can work with the incompressible substance model. And I'll just leave you with a problem as well, just so you can practice with it and try and evaluate this problem as well through um, the incompressible substance model. Uh, just go through this problem over here. The uh, electrical resistor here transfers, let's say, X kilojoules of energy. So it could be, let's say, it's transferring about 150, let's say, kilojoules of energy to the system. And you have to find out the final equilibrium temperature in degrees Celsius. So obviously, again, you should be applying the energy balance on this. And yeah, that should give you a good start.